In the last few segments, we were talking about the case of pure bending, and in that situation we discussed what are the deformation and what are the strain fields, what are the stresses, and even in the last the previous segment we were talking about the radius of curvature. When a prismatic beam is under pure bending, it takes the shape of a circular arc, and we were discussing what will be its radius of curvature. Now, so those were about pure bending. The thing is, unlike the cases of axial loading and torsional case, you will find practical situation where a pure form of axial and pure form of torsional loading, many times you can approximate that they do exist. But in case of bending, it's almost always, it is not the case of pure bending. So you will have always transverse loads which will cause the bending. And we had discussed that as soon as we have a transverse loading, so the pure bending conditions do not anymore exist. But still, if we want to analyze a beam under such kinds of loading, then we discussed that we can consider a small segment and think that that small segment is subjected to a pure bending, and then do the analysis, and then and do the same thing for each and every segment in a way. Okay, but then for doing that, you will have to know how much moment is actually acting at every such segments, right? So that's one of the reasons why we need to visualize the bending moments which exist at every point on the axis of the beam. And so basically, if I draw a parallel between what we did for axial and torsional, so after doing the pure cases, we went into cases where we will have lot of those moments. Maybe this is just for completeness I am pointing it out, but very soon, very quickly, we will get into the shear force bending moment diagrams. Yeah, so for example, like this, say M1, M2 and M3, if such cases, multiple load case exists, then you know what to do so that you can segmentize things, and each of those segment again is of our pure bending case. But as soon as we come to say cases like this, where say there is a moment, here there is a moment, but then suppose here there is a force and here there is a continuous kind of loading, and then you lose the case of pure bending. And then, as I was just mentioning, you have to talk about at a distance x, if I pick a small segment of delta x, there if I want to think that this particular segment is under the action of this moment, but at that location x. Okay, so then I can talk something about, okay, what will be the radius of curvature at that location, and all that thing I can talk about in a small zone. But to know that, I have to know that moment at that particular location. So basically, that means we are tackling the problems of this type. So that's our aim, and with that objective, we are trying to see the variation of the moment, and then the primary aim is to see the variation of moment with respect to x, but we will also see the variation of the shear force with x in the same stretch, because as soon as a transverse force comes into picture, even the shear force exists at every location. So that also we will see the variation of this and the shear force and the bending moment, and that graph or the plot of variation of shear force and bending moment with respect to x are called the shear force and bending moment diagrams. So SF and BM, that is shear force and bending moment diagrams. Okay, so shear force and bending moment diagrams are the things which we are going to discuss. They are nothing but they are graphs between x on the abscissa, and here you have curves, either shear force or bending moment. Okay, the bending moment means the moment which is trying to bend the beam at that particular location. So this is basically the point of discussion for this segment. And I would just like to point one thing, that this is one such concept where how to draw or how to do a thing is as important as why to draw the thing. Okay, now why is, anyway we discussed why are we drawing this, but then how to draw is also very important. Okay, so let's see what do we mean by, so then the question of what are we drawing. So what are we drawing are these moments and shear forces, and then in a moment we will see what exactly do we mean by that, and then how to draw is the skill which you need to develop, and then we have discussed why are we drawing this. Okay, now as soon as we start thinking about how to draw the SF and BM diagram, it's the basic principle is very simple. It is just like again FBDs, nothing except FBDs, and the principle is very simple. Let's discuss that. Suppose you have a beam where there are multiple say forces are acting. Let me draw say a force here, say a force here, say F1, F2, say a moment here, and some other continuous forces. So I'll just tell you something about this. Mostly beams are subjected to some continuous loading, not only these kind of concentrated forces, maybe F3 here, or concentrated moment like that at a particular location, but a load which is varying continuously along the axis for a certain duration, or maybe even the full extent of the beam. Okay, so these are very common, and then continuous and uniform I have shown here, and then we will see later that there can be even cases where continuously linearly varying forces also may be coming, and so on and so forth. And then whenever these kind of drawings are shown, they mean continuous loadings, and that you always express as density of the force, that linear density, that is weight in either kg per meter or Newton per meter, whatever. So in the linear density form it will be expressed, and then you will have to evaluate the actual load that comes into the beam. Okay, so that was about the representation, and this is a representative configuration on which we will discuss what exactly do we mean by shear force and bending moment diagram. Okay. Now, so as I mentioned, it is just the graph on which the x-axis is the x direction. Suppose I define my coordinate system's origin here, and this side is x. Okay, and the maximum length is say L of the beam. Okay, so x varies from 0 to L. Now, so that means here I will require the diagram to be from here to here maybe. Okay, so x is equal to 0 to x is equal to L. Now, I have to draw here. So generally what is done is you draw both the shear force and bending moment diagram and in fact the beam with its loads one below the other. Okay, so here while explaining I am not drawing the beam also there, but once we go to the examples we will actually draw everything one below the other, and there is a reason also why it is drawn like that, and we will discuss that in the next segment. Okay, now if I draw the beam again here, the x-axis for drawing the bending moment. So here again I'll say this is my x is equal to 0 and here is my x is equal to L. Now this part is my drawing for bending moment. So here the y-axis is my moment, bending moment in Newton per meter maybe, and here we are having shear force in in Newton. Okay, and now we are trying to draw the plot of shear force. Generally it is represented as Vx and this is as Mx. Okay, shear force and bending moment. Okay, now what do we mean by drawing this? Let's see. So the point is, the basic principle is that how much of force that is actually trying to shear the beam at any location at x. So that is the shear force diagram. Okay, that means suppose if I come to say this location at x. Okay, suppose this distance is x from the origin. Now if I draw the free body diagram of this portion, which will look something like this, right? And here I will have the force here and here the uniform force, and then these are the external forces which are coming onto the free body diagram. Then we will have to show the forces which are coming from the right hand side, which we have now thrown away, right? Free body diagram, we have cut a portion. Now we have to compensate this with the forces which were coming earlier from the right hand side. That is how it will be in balance, right? Now then here you will show that the shear force V, so one force and a moment can come onto this. So this is the force and this is the moment which you now are assuming that were coming from that. And here there is a convention which is very important to be aware of. Now the sense of these forces which I have drawn, force or moment, these are considered to be positive when you keep the left portion of the cut section. Okay, suppose you have cut it somewhere and you have kept the left side of the thing, then you have to show or you have to assume that shear force is acting in this direction and moment is acting in this direction, and these are considered to be positive. If the value which you get after drawing like this, you will calculate the V and calculate the M. Then if the value, the numerical value, if it comes out to be negative, you will say that the sense was exactly opposite to that you have assumed, but you will start with this being positive. Okay. And similarly, if and the point is, see, free body diagram of the left is equally valid as the free body diagram of the right side portion. You could have as well thrown away the left portion and just kept the right side portion as the free body. I'll just draw it here again, so that for example you could have kept the right side portion, okay, and where what are the forces. So this is one force, this is one moment, and this is another force, okay. So let me write them. This is M1, this is F3, this is F2, and similarly here say F1 and here W. Okay. Now if you want to keep the right side portion, okay, so once you solve some problems, you will then will get an idea which portion to keep when. It is just a mathematical convenience, okay. Any side is equally valid, but then you will understand slowly by practicing problems that which side is convenient, so that you can get the number easily. Okay. Now if you keep this side of free body diagram, so I'll just write it here, say FBD version 1 and this is FBD version 2. So anything is fine, any one is as good as the other one technically, but convenience wise one may be better than the other. Anyway, so now if you keep this, then the positive senses are like this for V and this for M. Okay, now I'll just put a demarcation maybe. So this is our for FBD1 and this is for our FBD2. Okay, so these are two possibilities of drawing the FBD, and from any of them you can get the value which will come and will be plotted here. Let's say we have kept this to start with. So what will you do? You will write the equation of equilibrium, which will tell you that say the V plus W times whatever this thing is, suppose this length over which it is acting is say it's delta, so then W times delta and minus F1 is 0. Okay. So this is the equilibrium equation for the V1, and from here you will just evaluate this, which will definitely come whatever it comes. So at that location x, so this whole thing is valid for this particular x where you have cut the section. Now then, so that means this V is a function of x, you can say that. Okay. Now at that x, so suppose that location is somewhere here, so you will just plot this V, that's it. Similarly, if you take say the moment about say this point, then you calculate the total moment of equation, right. So this I'll say this is the F summation of all the force in the y direction to be 0. So that gives you this, and similarly summation of all the moments about z will be 0 will give you the equation that say m, which is the counterclockwise, which you are calling positive at the location of x, because everything is at x now. Now this is again positive, say plus you can think that this W times delta is the total force, and suppose this is acting at a distance of whatever x minus delta over 2, right. So this times x minus delta over x minus. So this is full thing is x, and yeah, so maybe this distance also needs to be known. Okay, so forget it because I have just taken a representative diagram, so all the dimensions are not given here. So basically you have to find out this distance using the geometry of the problem. For that, here in this case you need to know this distance. Suppose this is say lambda, so I'll put here instead of this, I will just remove them, and then I'll put say lambda. Okay, and so that is also clockwise, but this one minus f1 times x is 0. So this equation, if you solve, you will get the value of m, and at the same location you will draw that. So this is m at x, this was v at x. Okay. Now, so that's the basic idea of drawing a point on the SF and BM diagram, and similarly if you can do the whole bunch of these things for different x's, you will get different points maybe, and so and then the curve which goes through those points is your shear force bending moment diagram maybe. So this is not corresponding to that, I am just putting something, okay, like that. So the idea I am just trying to now explain that what exactly does it mean, okay. Then we will just take up an example to solve this so that it will be completely concretized, okay. And then that's it. In fact, here you may be thinking that how many points do I need to plot so that I can get a reasonable good curve. It's not that. See this. If you consider sections between say discontinuities to discontinuities of force, then you can in fact say, suppose this example. So here something is ending and here something again is abruptly happening, F2 is abruptly coming, but then once you derive something as a function of x for any cross section here, you can say equal validity that this is true for any section which is taken in between, because it's a function of x now you have chosen and it will be valid there. Similarly, if you have taken a cross section say here, and if you have derived the equation in terms of x, that equation will be valid for everything that happens between this to this distance, okay, because one thing abruptly happened here and again something happened here abruptly, but nothing changed in between. So in those segment to segment analysis, if you draw, then segment to segment, segment by segment shear force and bending moment diagram you can draw in chunks, okay. So that is how you should draw, and then the full thing is your full SF and BM diagram. Okay. Now what we will do, we will just take the simplest of the example and just exemplify. Okay. Then in later segments we will do some more difficult problems where the idea will be even more clear. But the simplest example will be say I have this situation. Okay, here I will show you that how to draw it just one below the other. So you have the question like this. Suppose this is the beam, okay, and here you have the support. One end is here, the other end is here, and the load is exactly at the center, and which is F. Okay, so this length is L over 2 from here. I'll just use some other Okay, so this length is L over 2 and this length is also L over 2. So this is the condition. And you now have to draw the shear force and bending moment diagram. What is the meaning of that? That means you are drawing the graphs of the shear force that exists at any location and bending moment that exists at any location with respect to x or versus x. So for that, first you have to, what you have to do is you have to find out the ground reactions, so that this is the problem definition. Then below that you can draw the another drawing which can in fact tell you that you have okay, I'll draw the same thing. Evaluated the ground reaction and removed the supports in a way and replaced them with forces. So that now you know that how to calculate those forces and replace like this. And then that is why, if you notice, I have chosen the ground reaction in such a way that the beam will become a statically determinate structure. Okay, otherwise there was no way. In this case there are, because there is a symmetry. Otherwise in general case you cannot maybe find out all the 4 reactions. If I make this side also a simply supported thing, kind of thing, a hinge one, then there is no way you can figure out 4 unknowns. Okay, so that's why I made like this. So then you can figure out that all the reaction forces, and you will show here if this is F, obviously this will be F over 2 and this will be F over 2. And in your shear force bending moment diagram, all these important values should be shown. Okay, now okay, if I have to come like this, I always try to draw this way so that you will maintain the sequence. Okay, then I need to draw the x-axis for drawing the shear force and the x-axis for drawing the bending moment. So here the y-axis will be representing my shear force in maybe Newton, so V of x, and here it's say m of x, which is the bending moment, and maybe it's in Newton meter. Okay, so like that. Now what do we do? So there are 2 segments here. You remember we said that segment by segment is the method to solve these problems. Okay, because whatever happens in this section, the same thing happens anywhere you pick this thing. So segment by segment. Okay, now let's say we picked something at this segment, and this is our x. Okay, then you have 2 options to keep this side or that side, and we will try to see by keeping both the things. Okay, let's say we keep the left side portion. Now when see, let's say I'll draw it. Left portion FBD. Okay, so then what I have here, this is the thing like that, and I have, so let me draw here in this way also. Here I have cut, so then the forces to be shown are F over 2, yeah, and nothing else. And then I have to draw the conventionally correct positive shear force bending moments. This is V, and yeah, this is M. If I have to draw the right side FBD, I'll just do right portion, right side portion is better. right side portion FBD. Okay, and then I'll do this one, right, a big one. Then the forces. What are the forces? This is one at F, this full F at a distance of L over 2, and here this is F over 2 at this end. And if I have to draw the shear force and bending moment, they are like this, V and M. So these are the FBDs which I should use to calculate the V's, and any one is equally valid. No one is more correct than the other. Okay, let's say we are calculating with this. So first equation, what shall we write? Let me shift it a bit here. Okay, so now let's say for the shear force, so this is V positive minus F over 2 is equal to 0, implies V is equal to F over 2. So that's what you have calculated. Now let's see, are we getting the same thing here? Let's see, for the shear force we are calculating, say this one is positive, so V, then this side is minus F plus F over 2 is equal to 0. So implies V is F over 2, right? So in this case also you got the same thing which you got it here, and now you see that in this segment wherever you pick this x, the same value you will get, and in this case specifically it's a constant, it's not a function of x, it's a constant. So let's see, so that means if we want to draw the shear force here, we can just simply, and it's a positive F over 2, so we will just draw up to this point, right? So let me put, it's a good practice also to just put these lines for all the segments at the beginning. Okay, so now at F over 2 you have these values. So this is, at F over 2. Now this segment is done for the shear force. What about the other segment? Before that, shall we draw for the bending moment also? For the bending moment equation, if I have to write here, say M, suppose I am taking the moment about this location. So moment M counterclockwise is equal to, or I'll write in this form. So minus F over 2 times x is equal to 0, right? Implies M is equal to Fx over 2, right? And so here you see, in the shear force case it was a constant value, but now you are getting a function of x. But over the whole section, as a function of x the value of m, so you can actually draw it, right? So when x is equal to 0, you are just at the beginning, so the m is 0, and when you go to x is equal to L over 2, you have FL over 4. X is L over 2, right? So that's it. So from here 0, I'll use this one. So like that, and this value is, say, FL over 4. So it's drawn. Shall we do for this also, to just show once that even if you use this side, you will get the same answer. Now if I say this, so now M, in this direction I am taking moment about this, and minus and this is plus F times so this distance is how much? This is L minus x minus L by 2. So okay, this is L by 2 minus, okay. So L over 2 minus x plus minus F over 2 times L minus x. It is equal to 0, right. So you just saw this now. This equation was very simple and this equation is a bit clumsy, though this is not very clumsy, but as compared to this it is complicated, right. But let's see, are we getting the same thing here? So FL over 2 and FL over 2 cancels out, and then here minus fx and here plus fx over 2, so minus fx over 2, so this side, yeah. So m is equal to fx over 2. Again you are getting the same thing, but now you are solving a more complex equation, the thought process is more. So that is what I was talking about, that the same thing you will get, but you have to think about which side you should calculate, so that the calculation will be little bit easier. That is it. So this side is done. So the same thing when you draw for the other side segment, I'll just draw the FBDs and then you can see that how it will be done. And so now what has happened, your x is somewhere here, okay. So this is your x now. So the left side FBD if I put, so I'll say left side FBD. So how will it look like? So now it's a longer side, this one, okay. And then the forces are, what are the forces? Here it is F over 2, here it's F, that's it, and the shear forces are like this, and bending moment. Fine. And then exactly in the same way you have to write the equations of force balance and moment balance, and you will get the equation for this portion, okay. Yeah, so I think, let's say we will just do for F here. What would you get? So this is V and this is M. So now V minus plus F minus F over 2 is 0, implies V is negative F over 2. So this is very important. See this? So you have got now a negative value, so that means here it was positive, so here you should have actually, yeah, I don't have space here, I am just squeezing it here. So this is, you know, minus F over 2. So these important values you should always show them on your shear force and bending moment diagrams, okay. In fact, yeah, so this is your, okay, this should have been exactly the same height as this one, okay. Fine. So then how to calculate for M? If you calculate that, you will just see that you will get the curve for this, okay. So that will be your complete shear force and bending moment diagram, and this is the method of calculation. And then again I am repeating, you could have done that very easily by taking the right side portion also, exactly the same answer you will get. So we will stop here for this shear force bending moment diagram section, and we will meet in the next segment. See you.